Okay, so for today, our topic, we're going to focus on this redox indicator. From the name redox indicator, reductions and oxidations. Reductions and oxidations. Okay. So what we're going to do for today, we're going to look at two processes that involve redox, which is respirations and photosynthesis, because we know that there is electron flow. Okay, that is electron flow. Therefore, we're going to look at this redox indicator, how this redox indicator can help us to determine the rate of reactions, okay, under a particular condition. So for example, we look at the photosynthesis, we look at these three factors: light intensity, correct? We also look at the temperature and CO2 concentrations, okay, in terms of the redox indicator. What redox indicator can do? If let's say we talk about respirations, then we focus in terms of the temperature. Okay, so let us look at the learning outcome for today's lesson. So first of all, we need to know how to carry out investigation to determine the effect of the light intensity or light wavelength. So we can use the two different light intensity. Either we constant the light intensity and then we adjust the light wavelength. For example, the wavelength start at 400, 420, 440, and so on until 700. Okay, so when you plan for the experiment, very, very important right now. If you need to involve the light wavelength, okay, you need to involve the light wavelength. Always remember the wavelength should be in between, okay, 400 nanometer to 700 nanometer. Okay, right, let me write down. Okay, right now, guys, if you plan for experiment, so wavelength that we use, it must be from 400 to 700. Anything less than 400 or more than 700 is not correct, because this is a visible wavelength. Are you clear? The visible light wavelength. Okay, so don't give me anything less than 400 or anything more than 700. Okay, so it means that you decide experiments, okay, 400, 450, 500, 550, and so on. So if you want to use this, okay, for the wavelength, be careful. Okay, don't simply give me 0, 10, 20, 40. No. The units nanometer, sorry. Okay, write down, the units will be nanometer. Okay, so we look at the photosynthesis. So these reactions actually is the Hale reaction. So in textbook, you can see that we have this Hale reaction that I haven't covered yet. So, but now I'm going to talk about these Hale reactions later. Okay. Then we also can carry out investigations to determine the effect of the factors such as temperature. It might be substrate concentrations on the rate of the respiration, rate of respiration of yeast using the redox indicator. So what redox indicator can do? When we talk about redox indicator, for example, we're going to use DCPIP, okay, or we can use the methylene blue, these two, okay. Please make sure that you remember the name of these two. DCPIP. DCPIP, you do not need to give me the full name of DCPIP, okay, or methylene blue. So redox indicator, actually they can change color. So it depends on whether they are in the oxidized state or reduced stage. Are you clear? When they are reduced, they may become colorless, or they may oxidize, they become colorless. So it depends on which types of the redox indicator that we use. Okay, so DCPIP is a little bit blue color, methylene blue from name, yes, blue color as well. So we're going to look at how both of them functions to help us to determine the rate of reactions. Okay, so I will go into it detailed now. Let us look at this. So when we talk about redox indicator, also known as oxidation reduction indicator, is an indicator we use to undergo a definite color change at specific electrode potential, or I call it as a oxidation stage. Okay, so the requirement for the fast and reversible color change means that the oxidation reduction equilibrium for an indicator redox system needs established very quickly. So it means that if you want to look at the process, the best way to determine the rate of photosynthesis, definitely we look at how much O2 can be collected per unit times, correct? If we talk about the rate of the photosynthesis, we always want to collect the volume, okay, to measure the volume of oxygen released per unit times. Okay, so write down for rate of photosynthesis. We always want to collect O2. Okay, by what? By downward water displacement technique, for example. Okay, to collect O2, then we get the volume of O2, then we can actually use the volume of O2 over times to calculate the rate of photosynthesis. Correct now? Okay, how about the rate of respiration? In order to calculate rate of respiration, against now we collect, okay, CO2, okay, by downward water displacement technique. Correct? Okay, and then by have the volume of CO2, and then we can calculate volume of CO2 per unit times. Okay, this is the rate of respiration. Or we can also find out how fast we use O2. Correct? Okay, how fast we use O2, something like respirometer. Okay, but sometimes we want to have a very quick rate of respiration. We don't want to collect it based on how many hours, or maybe we want to collect it for small mammals, small animals. We may need to prolong the times. Correct? So therefore, we want to have a quick indications of the respirations of photosynthesis. We always can use this redox indicator. So example of this redox indicator highlight DCPIP, we can use it. So highlight this part. When oxidized, DCPIP is blue. Okay, when reduced, DCPIP is colorless. Okay, try to remember. Oxidized stage, DCPIP is blue. When reduced, means that the DCPIP now become colorless. Okay, so how we do this? So during DCPIP, can be used to measure the rate of photosynthesis. It's part of the Hill reagents family, Hill reagent family. So when exposed to the light in the photosynthetic system, the dye is decolorized by chemical reduction. So why this actually happened? Then we have to look at the rate, the photosynthesis, particularly non-cyclic photophosphorylation. Okay, so let us look at this. Okay, a quick revisions. So we have the photosystem 1. Okay, so upon the receiver, the photons, the light energy, so electrons will be photo excited. Okay, photo excitation of the electron actually take place. Correct or not? Okay, then this electron will go through a series of electron carrier, okay, or electron transport chain. Either you say that go through pass these electrons pass along the electron transport chain, or a series of electron carrier, and finally received by who? Received by NADP. Okay, NADP together with the electron, together with the proton, then they form the reduced NADP. Can you see that? Okay. So always remember, the first process, actually electrons have to combine with the protons, and then only they accept by the NADP. So to form this reduced NADP. So what Hill reactions or DCPIP can do here? Okay, so basically DCPIP now compete together with NADP. So DCPIP in the oxidized stage, they are blue or purplish color, blue or purplish color, okay, blue. But when they receive electrons, so means that DCPIP in the oxidized form, because they compete, can you see that the DCPIP now compete with the NADP for the electron. When the DCPIP receive the electrons, means that now is reduced. So it becomes the DCPIP in reduced form. So the DCPIP in the oxidized form, as I said, that's their blue color. or purple color, when they reduce to DCPIP reduced form, they become colorless. So what we can do, actually, we can get the times. We can measure the time, how fast the decolorations take place. Are you clear? How fast decoloration take place. Then we always can have the rate, which is equal to the 1 over T. This is how we calculate the rate based on this formula 1 over T. Now be careful, 1 over T is just a what we call this, a simple way of the calculation. So it depends on the rate determining factor here. Are you clear? What we call this constant, right? Rate determining constant. So this one actually is something like for us to for easier calculation. So it's not necessarily must be 1. It depends on the question. Sometimes question says 100. Sometimes question will say 1,000. You just follow the question how we calculate. Okay, so this is how we carry out the experiment. So the basic principle is very simple. DCPIP, they are colored in the oxidized form. Okay, so DCPIP going to compete with this NADP for the electrons. So when DCPIP take the electrons, then it become colorless. Why? Reduced form, right? When it take the electrons, it become the reduced form. So it become reduced form, then definitely colorless. So we take the time, how fast color, okay, change or decolorations of the DCPIP take place, and you can calculate the rates by using this formula 1 over T. Okay. So this PIP has a higher affinity for the electrons compared to the ferredoxins. Okay, it competes, and the photosynthetic electron transport chain can reduce the DCPIP as a substitutions for the NADP. So it competes. So that's normally the final electron carrier in the photosynthesis. So as DCPIP is reduced and become colorless, the resultant increase in the light transmittance can be measured using a colorimeter. Okay, so 2 ways we can actually measure we set the time. Okay, we set the time. Let's say, for example, we set 5 minutes. After 5 minutes, we check for the light transmittance, okay, or light absorption. Or we can measure, straightaway measure how fast the decoloration takes place. Okay. So methylene blue is also widely used as a redox indicator in the analytical chemistry. So solution of this substance against blue when they are in the oxidized form. Okay, again, blue in the oxidized environment, but again, they turn into the colorless is exposed to the reducing agent. Okay, so for example, electrons. So normally we use this blue, methylene blue, blue color, methylene blue, where we use it for the respiration. So in respiration, as the rate of respiration increases, the concentration of products produced per unit time by the dehydrogenase enzyme in the cells will increase. So more methylene blue can be reduced at a given time. So we can check it on the optimum temperature. Then we can see how fast this methylene blue can be decolorized. Okay. So one thing that we need to be careful. Okay, let me show you guys something. So in order to perform this experiment, first, as usual, we put in a control. Right? We need to set up the control. Let's say, for example, our factor here is the light intensity. If we want to check the effect, or check the effect of the light intensity, so we set a control, okay, to make sure that the decolorations of the DCPIP is due to the light, not because of the temperature, not because of other factor. Are you clear? Not because of other factor. It's set a control. So this control we term it as a negative control. Okay, we term it as a negative control. Means that no light. Are you clear? No light. Okay. Now, second, we need to set up another control termed as the color control. Now, why we need this color control? Now, how we set up this color control? Okay. Now, then we have to look at the experiment now. So first process, what we need to do, we need to carry out the extractions of the chloroplast. Now, compared to the last week practical, last week practical, we extract the chlorophyll. We extract out the photosynthetic pigment. When we extract photosynthetic pigment, then we can actually separate the pigment, and those pigment, they are soluble in the organic solvent. So that's why we use the acetone, we use the ethanoids, okay, those organic solvent to extract the pigment. But for today, we extract the chloroplast. Are you clear? So we extract the chloroplast. Okay, pigment is not enough. Okay, so how we do it? Again, so first step number 1, we need to, use pestle mortar. Okay, in this case, okay, we can use a pestle mortar. If don't want, you can use a blender. So basically, we want to break sour. Okay, break the sour. Okay, and also the salt membrane. Okay, so how we break it? So we use the buffer solution. So this buffer solution actually contains 2 important components. So that first thing, we have to control the osmotic property of the chloroplast. We want to maintain osmotic property as well as pH. Are you clear? Okay. So why we need to maintain osmotic property? Because chloroplast, okay, you try to imagine if we put in the buffer solution. So for example, this is our blender. We can use a blender. Okay. So what we're going to do, we put in the leaf. Okay. Put in a leaf. Then we put in this osmotic buffer solution. Okay, not so high. Then we spill. Okay, you put a certain volume of the osmotic buffer. And we start to blend it. Okay, we cover. And then we start to blend it. Are you clear? So after we blend it already, then we're going to filter. Okay, so that you get the chloroplast extract. Are you clear? Chloroplast extract. Okay, so we put a muslin cloth, and then you can see that those debris will be accumulated here again. Okay, accumulated debris. Okay, but we have to make sure that everything, you must done it on ice. Now, why do we need to be on ice? Now, in this experiment, we want to maintain the integrity of the chloroplast. Means that we don't want chloroplast to lyse. Are you clear? Okay, why chloroplast will lyse? Because when you lyse the cells, okay, you're going to release enzyme. So this enzyme will be released into this extract and going to spoil the chloroplast. In order to reduce the rates or the degradations of the chloroplast, we need to put it on ice. Always remember, we prepare everything on ice. So once we get the chloroplast extract already, always remember chloroplast extract actually is green color. Okay, it's a green color. Okay, so what we're going to do now, so for each light intensity, okay, for each light intensity, what we're going to do, so we set up this way, okay? So the first part already done, already, extract the chloroplast already. So second part, we run the experiment. Okay, so today, very simple. We just want to know the rate of reaction for one light intensity. Okay, so let's say we set the light intensity. Okay, let's say, for example, I set it at 10 units light intensity. Okay, 10 units light intensity versus no light intensity. No light. Okay, so it means 0 units. So 0 units will be our control. Clear enough? Okay, no light compared to the light intensity here. Okay, so how we set up the experiment? First thing, so we put our tube. So we add in our buffer solution. Okay, we add the buffer solution. We cannot put distilled water, yeah? Okay, distilled water going to burst. Okay, distilled water going to burst our chloroplast. And then we add DCPIP. Okay, and we add the plant extract. Oh, sorry, chloroplast extract. And we mix that. Okay, so what we're going to do, then we actually give a distance. Okay, let's say, for example, 10 centimeter. Okay, 10 centimeter. So you put your lamp here. Okay, then we start to use our stopwatch. Okay, our stopwatch to measure to get the time, how fast the decoloration take place. Okay, but in this process, we place it under light, right? 10 centimeter. Okay, so what happened here is we have a trigger some question. First question or first issues, how you know that DCPIP is completely decolorized? First question. Okay, it's not like, because we have to know with chloroplast, the entire solution is a mixture of the green plus blue color. Why? Blue color because DCPIP chloroplast is a green color. So it's a mixture. So how you know? It's not like, I mean, some of the experiment, you will know this is totally decolorized because you won't see any other color. It's totally transparent, but this one, no. So therefore, we need to set a solutions here. We need to set a color control. Are you clear? We need to set a color control. So this color control will contain what? This color control, okay, will have the buffer solutions. Okay, with plant extract only. Sorry, chloroplast extract. Why is it? Are you clear? So to tackle the first question here, so DCPIP is how we know the DCPIP is completely decolorized, then we need to set the color control, then we can compare. Can you see that we can compare? Are you clear? We can compare now. Okay, DCPIP. Okay. Second question. How you know that now the decoloration of DCPIP is due to light intensity. Okay, sorry, due to the chloroplast or light intensity. How you know? The decoloration of DCPIP is because of the chloroplast or light intensity. Then we need to set the negative control. So now what has been negative control? So we have to do two negative control here. Okay, two negative control. One negative control actually for the chloroplast. So how we know? So very simple. We have the tube. We still put in the buffer solution. We still put in the DCPIP. Can you see that? And then here, no chloroplast extract. So this tube at the end will show us the DCPIP won't be decolorized. Are you clear? And then we need to set up another tube to show that because of the light, cannot because of the light. So in this case, we're going to do what? A tube with buffer solution with DCPIP, and we put in the chloroplast extract. But no light. Can you see that in the dark room? So in this case, you won't see any decolorations if, let's say, because of the light. Can you see that? So we need to set the negative control. Okay. But now we do have a little bit of problem here because of the concentration. Are you clear? Because of the concentration. Okay. Now try to imagine that buffer solutions here will act something like a solvent. You look at buffer solution, buffer solutions, buffer solution. So if you have the same amount of buffer solution, then you can see that because of the two different items here, the concentration will be varied. So it means that everything you have to understand that you must dissolve everything by using the buffer solution to make sure that the concentration remain constant. Okay, and normally when you say that, normally without the chloroplast extract, normally we actually replace it, right? So what we replace? We replace it with buffer. We cannot replace it with, okay? So it means replace the chloroplast extract with the buffer. So means we top up with the buffer rather than the chloroplast extract, rather than the distilled water. We cannot use distilled water because when you use the distilled water, you change the concentration. At the same time, also you change the water potential. Okay, so understand the concept here when you plan for the experiment. Okay, so what are the way we can change the light intensity? So in terms of planning an experiment, so to change the light intensity, we have few ways. So first, distance of the light from the tube. Second, we can adjust, okay, the resistance. Okay, and the resistance by using the what call this, the rheostates. Okay, or third, we can use a different power. Okay, that means the lamp with different power. Okay, so then we can change the light intensity. Okay, so normally easier way is a distance because the light intensity is inversely proportional with the distance square. Okay, according to the formula, the light intensity actually is inversely proportional to the D is mean distance, distance square. So it means that the further you put the lamp from the tube, therefore the light intensity will be lower. Okay, so let us go back to our notes here, the handouts. Okay, so this experiment, again, we can't do it. Okay, we can't do it. Just I'll go through with you guys first. I go through you guys, then no need to put in the data, but we can answer some of the question. So you're required to investigate, okay, the effect of the leaf extract or chloroplast extract on the solutions of the dye DCPIP. So the leaf extract will prepare as follows. So we have the fresh green leaf will homogenize, okay, with the chilled buffer solutions in a food mixer, or we can use the blender. And the mixture was filtered through several layers of muslin and subsequently maintained at low temperature. Can you see that ice cold buffer? And you have to put it on ice. Okay. And we do know that the dye DCPIP is blue when oxidized and colorless when reduced. So we prepared 3 tubes. Tube number 1, tube number 2, tube number 3. So volume of the buffer solution, can you see that different? 4, 5, and 4.5. Volume of DCPIP is 1 and DCPIP is 3, but no DCPIP for tube number 2. Okay, and then place the rack 10 cm in front of the bench lamp. Point the lamp at the tubes, but they do not turn the lamp on yet. Then you add 0.5 cm cube of the leaf extracts, okay, or chloroplast extract. So I put in this table, this is leaf extract in cm cube. Okay, only for tube number 1 and tube number 2. So 0.5, 0.5, and dash, no. So I want you guys to look at something. Oh, sorry. Wait, you realize that now why we actually make the buffer solutions have different volume? Because at the end, I want my total volume, they are the same, 5.5. Can I see that? Then when the total volume, they are the same, then we can make sure that the concentrations are maintained. Okay, so what is the functions of tube number 2? Can you see that tube number 2 without DCPIP? So this tube number 2 without DCPIP means that this is the color control. So it means that at the end, I should get the, okay, at the end, I should get the final color similar or same as tube number 2. Okay, and you can see that why 5.0? Actually, this 5.0 is 4 cm3 of buffer solution plus 1 cm3 of the replacement of the DCPIP. So 1 cm3 of this replacement here, we cannot use the distilled water. As I said that, if you put distilled water, you're going to change the water potential. So therefore, we don't use the distilled water to replace the DCPIP, but we use a buffer solution to replace the DCPIP. So therefore, you can see that 4 plus 1, you get 5 here. Are you clear? Okay, so we don't use the distilled water to replace the DCPIP. Now, what's the function of tube number 3? So you're going to look at the tube number 3. Okay, we have the leaf extract in tube number 1 and tube number 2, but tube number 3, no leaf extract. So basically, tube number 3 again is a negative control. So what's the function of this negative control? So this negative control is to show that later the leaf decolorations of the color, okay, decoloration of DCPIP is because of the leaf extract. So here, no decoloration take place. This is what we predict. So again, to replace the 0.5 cm3 of the leaf extract to maintain the concentration as well as to maintain the osmotic property, therefore we replace it with 0.5 cm3 of the buffer solution. So therefore you can see that here why 4.5, because originally 4 and 0.5, okay, as the replacement. So total we get back 5.5. Okay, we shake them, generally mix their contents, replace the tube on the right and turn on the lamp and start timing. So you time for 3 minutes. Record any change we will have observed in the contents of any tube during the times. Okay. So what you can conclude about the reaction A1 from the presence of the tube 3, and then explain why different volume of the buffer solution were added used in setup of the tube 1 and tube 2. This one you can answer the question, very simple. So the question that I want you guys to do is basically this. Okay, so you're required to investigate the effect of the light intensity on the reaction you have seen in A1. So you are given a piece of muslin cloth and aluminum foil. So this can be placed around the test tube and secured by using a rubber band or transparent tape so that the different intensity of the light will fall on the content of the tube. So now, just now I said that to adjust the light intensity, we have few ways to do it. First way, we can actually put a distance, okay, 10 cm, 10 cm, 20 cm, 30 cm, and so on, right? But in this question, you are restricted by this step. Means that you have to use the given items, okay, and secure them by this rubber band. So it means that you can wrap around this test tube so that you create the different light intensity. For example, if you use aluminum foil, so it means that 0 light intensity. Light cannot penetrate through the aluminum foil. If you use a muslin, then you wrap it one layer of the muslin, so you actually have the partially. Okay, I don't use the word semi, okay, partially. Okay, the light intensity can partially pass through, and another tube we're going to set up without the anything, okay, without the muslin and without the aluminum foil. So make sure that it's totally transparent. So we create 3 different conditions. One is fully transparent, one is fully opaque, basically means that the light cannot pass through, and we have another one is partially by using the muslin. Okay, so in this case, how you actually can come out or design a procedure that you adopted to make your conclusion become valid. So be careful when you want to be valid, make sure that you must have a control. Okay, must have the control. So think about this, what you want to measure. Time taken, or you want to observe. Okay, observe or measure the intensity, color intensity after a fixed time. So which one? So it must be logical and detailed enough to let other person to follow. So which one, guys? Which one? Time taken is easier, or observe it or measure using a colorimeter, okay, the color intensity at a fixed times interval. Let's say, for example, after 3 minutes, you measure the light intensity. Which one is more possible? Time taken, or you observe, or you actually read the color intensity or determine the color intensity by the colorimeter. So it must be logical. If you look at this, you are going to wrap them with aluminum foil. You're going to use a muslin, so you can't see the color change. So how you determine the time taken? You cannot keep on open, close, then you have extra light intensity, right? So you cannot open and close it. Okay, remove the aluminum foil, look at it, and then close. Okay, then you may miss the time, the complete decolorations, correct or not? So what we're going to do here is we need to set the time to check for the color intensity. Let's say, for example, for 3 minutes. So after 3 minutes, we stop the reaction, place them in the colorimeter to check for the color intensity, or a simple way, we compare to the color chart. Are you clear? So this is the one that you need to think when you plan for your experiment. Okay. So record result, definitely you can't record, and then state the conclusions. Again, you can't state any conclusions. So you can answer this question, guys. Okay, use your biological knowledge and your observation, explain the effects of the leaf extract on the DCPIP solutions. Okay. So what other factor may affect the rate of reactions? And this is very important, why we need to maintain pH at 6.5 and why we need to include sucrose in our buffer solutions. Okay. So when done this one already, then you can continue with experiment 12.2, which is a past year paper. Okay, you can try this. Okay. So with this, I have done for the